Well, so welcome everyone to the August XAFS Journal Club. Jerry's viewing, but on vacation in a way, so he asked me to moderate this edition of the XAFS Journal Club. Today we're pleased to have Nirala Singh from Chemical Engineering Department at the University of Michigan. Nirala got his PhD from UC Santa Barbara a few years ago and is now an associate professor at University of Michigan. And he's going to talk about electrocatalysis and electrolytes in fuels and flow batteries. I'll remind everybody, if you have a question during the talk, we have 2 breaks scheduled. And if you have a question, just put it in the chat and I'll call on you at the 20-minute mark or the 40-minute mark as we go. Okay, so Nirala, welcome, and please tell us everything you know about electrocatalysis.
Yeah, thanks, Matt, and thanks everybody for joining. So this is just a photo of my group at University of Michigan. The work that I'll be talking about is a combination of kind of work that I did that I've been doing at Michigan, and then also work that I did as a postdoc at University of Washington in Pacific Northwest National Laboratory. So that I was co-advised by Charlie Campbell and Johannes Lurcher, and then I worked with a lot of the other postdocs and staff scientists, and in particular John Fulton I worked with to do a lot of the X-ray absorption measurements that I'll talk about there. At I think every XAFS measurement that you'll see, it was done at Argonne with Dr. Mali, who was I think maybe a presenter maybe a month ago or so, and then I didn't have a photo of Chengjun, but he's been helping us more recently. And then the redox flow battery work was done by 2 of my PhD students, Hirsch Agarwal and Kaylin Buchanan, and then the simulations were done by Professor Brian Goldsmith, and we had some funding for that. So really the 2 kind of stories that I'll be talking about today. The first is generally on this concept of electrocatalytic hydrogenation. So the big picture idea is we want to take distributed biomass, so basically maybe woody portions of trees, these kinds of things. If they're pyrolyzed or converted, they'll form a aqueous stream that's sometimes referred to as bio-oil that has a lot of these organic molecules. And what we're interested in is using electrochemical reactions to hydrogenate some of these aromatic rings on nanoparticle surfaces and then convert them to things like jet fuel. So that's really the overall goal of these types of projects. And how we use XAFS is we use it to interrogate these nanoparticles when they're interacting, basically trying to understand the electrocatalyst structure, and then also what is adsorbing onto those electrocatalysts. So that was a lot of work that we did at PNNL and then continued on a little bit after it and still doing work at Michigan. And maybe I'll give another example of other ways of doing hydrogenation beyond biomass. The second part of the talk will be on redox flow batteries, where basically we're storing electrical energy in electrolytes. So in this case, we are studying the structure and basically the water and anion coordination of metal ions that are used to store electricity. So the difference between a redox flow battery and something like a lithium-ion battery, all the charge is being stored physically in the electrode through the intercalation or through a deposition or something like that. In this case, the electrolyte is separate, and the energy is stored there, which gives you kind of a decoupling of power and energy demand. And what we found is that the electrolyte will influence these metal ions and their structure, and then through XAFS we can identify that and see how it affects performance of battery electrolytes. So we'll start with first thinking about a model reaction where we're trying to take phenol, bring it to cyclohexanone and cyclohexanol. So phenol is like one of the types of compounds that you might see after decomposition of lignin. And again, we have a catalyst here that might be something like a platinum catalyst or palladium catalyst. We're taking protons from water or acid, reducing them with an electron, forming these hydrogen species, and then trying to react the phenol. So that was really that's when we see a reaction rate, that's what we're doing. And what we've noticed is that electrocatalytically, meaning you put electrons in to do this reduction, or thermocatalytically, where you just feed high pressure hydrogen into these systems to give these hydrogen equivalents, there's a very similar mechanism based on the activation energy from the rates, all these kinds of things. So we have a picture, or what we think is happening is that these phenol molecules are adsorbing onto the electrode surface, sorry, the electrocatalyst surface, interacting with these hydrogen species, and then converting. And we know, obviously, we can study the reaction rates of this and have kind of models. So some of the things we've done is we've said, okay, as we change the voltage, what happens to the reaction rate, the turnover frequency, basically how many phenol molecules are converted per second per platinum or rhodium site. And we can see things like as we go to more negative potentials, the rate goes up. As you go to too negative of potentials, the rate starts going down. And this is qualitatively similar to what you might see as you increase the hydrogen pressure. So really the picture of this, or that we would think from the model, is that you have hydrogen and phenol that are both on the surface, and at low voltage, voltages, I guess more positive voltage here, or a lower hydrogen pressure, you don't have enough hydrogen on the surface. Then as you go either more negative or higher in hydrogen pressure, you can force some of this hydrogen onto the surface. When hydrogen and phenol are both on the surface, they can react. And then the reaction occurs, you get your hydrogenation. If you go too extreme, you put too much hydrogen on the surface, there's no room for the phenol, and the reaction shuts off. So this was kind of the thought for this system, and it's described by what's called a Langmuir-Hinshelwood mechanism, where you have adsorption of the species, hydrogen, phenol go onto a catalyst surface, you undergo a surface reaction, and then a desorption. And what we found is this surface reaction is kind of limiting the overall rate. So you can write your rate law as some rate constant, and then however much hydrogen is there, however much organic is there, right? And you want those to be kind of evenly distributed. If you have too much phenol, no good. If you have too little phenol, also no good. And that's really dictated by just the adsorption energies of these things, so how strongly they absorb. I won't go into how we measure the adsorption energies here. I want to focus more on how we probe these nanoparticles under reaction conditions using a cell that John Fulton and I built at PNNL when I was there. And so this is basically a system where we can take those nanoparticles, put them onto a carbon felt, and then load them into an electrochemical reactor that allows you to separate your cathode and your anode. So the cathode is the one doing the reduction. The anode is just really doing water oxidation there. So we can load this kind of packed bed of system into here. So this is like a cartoon of it. Its catalyst is loaded here. We can feed electrolyte in so that we have all the species doing the reaction. We can control the potential through these things. We have a reference electrode that allows us to control the potential. And then we hit it with an X-ray and either do fluorescence or transmission, depending on the conditions. And we can take spectra of the platinum catalyst or palladium or whatever we want to study while it's doing the reaction. So really, we're interested in probing this Langmuir-Hinshelwood mechanism under reaction conditions. That's what we're kind of interested in. So this is what it looks like at the APS, Advanced Photon Source. We pass the X-rays through here. You can't see these inlet ports, but there's a syringe pump feeding electrolyte in there, mostly to remove bubbles. So if you just let this sit, if you are under reducing conditions, you'll slowly build up formation of H2 molecules, right? So if those H2 molecules accumulate too much, they'll form H2 gas. But if you flow electrolyte through them, the H2 molecular hydrogen that is formed is solubilized, right? And then it can exit without affecting your transmission or your fluorescence measurement. So really, we're able to monitor this, and then out of the hutch, we're controlling the reaction potential so we can do all these X-ray measurements, control the potential to more negative, more positive, test these kinds of things. So this is really the Zane spectra of the platinum edge as we're doing this. So since these are nanoparticles, as we prepare them, or as we load them into the system, you can see that there's some additional white line from the oxidation state of the platinum. So these are really platinum nanoparticles with the surface platinum oxide. As soon as we put an applied potential to them, so a negative applied potential, they go from being surface oxides to metallic, and we just have the platinum foil there to surface this. So this was one of the questions when we're thinking about what is the catalyst surface under these operating conditions, and we can tell, okay, it is a metallic platinum when we're doing the reaction, even though as we're walking around with these catalysts in the air, they're partially oxidized. The other feature here is that you might be able to see in this red line of the platinum nanoparticles is there's kind of an additional portion in the Zanes associated with hydrogen adsorbed onto a platinum surface. And this is kind of well documented by by some groups that they know, once hydrogen adsorbs, even though obviously the X-ray absorption is a bulk technique, if you have few enough total, a small enough size, a high fraction of the platinum atoms are at the surface, so you still see a lot of these features. And this is really related to how much hydrogen is on the surface of the platinum. So what we did is we took this spectra and then just subtracted it from the platinum foil to basically see these differences, and then plotted this difference here. So this feature in blue is just when there's no phenol at all. The difference of this is attributed very nicely to the hydrogen that's adsorbed to a platinum nanoparticle. And if the hydrogen was not adsorbed there, this feature wouldn't appear. So it's basically telling you how much hydrogen is adsorbed. And this line that you've seen is also why we think it's platinum and hydrogen, is that Nirala Singh, who's also at PNNL, did X-ray near-edge simulations using time-dependent density functional theory that basically said, if you put hydrogen atoms onto a platinum cluster, this is where they should show up. So it's kind of telling us, confirming that, but many people have done it experimentally before. And then what we noticed is because if you recall, this syringe pump allows us to control what goes into the cell. We basically went from no phenol at all, so just an acetate buffer, to 1 millimolar of phenol and then 20 millimolar of phenol. And then we can see that as we add this phenol, while keeping the potential constant, we see that the hydrogen peak goes down, and it becomes this other type of peak here that what we attribute to platinum carbon interactions from the phenol starting to adsorb. So you can see the hydrogen portion goes down and this other feature goes there. And Neri also did some simulations where he put carbon there, did the time-dependent DFT that kind of corroborated, oh, these would have different peaks here. So this is really a picture of us seeing the phenol and hydrogen competing for sites at a given potential on the electrocatalyst surface, right? And then what we can also do is we can do the extended fine structure of this, where we saw that in this region at a very kind of low distances, this scattering feature. So this is the normal scattering feature that tells us the nanoparticle size, that the distances are all matching. But the interesting thing that we noticed is that when you add some of this phenol, there's a feature here that also goes up that we attributed to the scattering of the surface platinums with carbon around them. So there's always some small amount of it there that we think is because these platinum nanoparticles are supported on carbon, like a carbon support, but that further went up when we added phenol. So we ran molecular dynamics simulations of this, and this is kind of a picture of what we think is happening. There's hydrogen on the surface, phenol can come there, and then you see all these phenol molecules are basically adsorbing flat onto the surface, and then a fraction of these platinum atoms will, in addition to seeing their neighbor platinums, they'll also see the carbon in that phenol. And when we looked at basically the fitting of this, we see the platinum phenol carbon distance matches what you would see for a phenol adsorbed flat onto a metallic platinum surface. So really this gives us a nice picture. The XAFS gives us a very nice picture of hydrogen is adsorbing, phenol is adsorbing, right? At a given potential, the platinum is nice metallic platinum. And then as we control the potential, or as we control the phenol concentration, we can tune how much phenol or hydrogen is on the surface. And this is why the reaction changes the way it does. It's because of this tuning of the system. And this really occurs whether we're doing it thermally, we're adding H2 gas, or we're doing it electrochemically. We did both of those at Argonne and saw very, very similar results. So this is kind of what's happening in these systems for phenol hydrogenation. The other one that we've done was study not platinum, but study hydrogenation of benzaldehyde on palladium. And the reason I show palladium here is that palladium, platinum, and rhodium, these platinum group metals, have been studied for phenol hydrogenation, benzaldehyde hydrogenation. And platinum and rhodium are quite good at phenol hydrogenation, and they're okay at benzaldehyde hydrogenation. But palladium was extremely good at benzaldehyde hydrogenation and very, very poor at phenol hydrogenation. So this is just benzaldehyde doing this. Again, we can control the potential. So more negative potential, the reaction rate goes up. But you can see the Faradaic efficiency, basically the fraction of electrons that go to benzaldehyde hydrogenation is nearly 100%, which is really extremely high. Just for reference, If we're trying to do phenol on platinum, only 40% of the electrons go to hydrogenating the phenol. The other 60% go to making H2 bubbles. So that's why we were having so much trouble. We needed to add these electrolytes to remove all the bubbles in the XAFs. Platinum also can do benzaldehyde hydrogenation, but it's about 50%. So it's nowhere near this 100% that we see here. So this is kind of beautiful for two reasons. One, it tells us that, wow, palladium is an excellent catalyst for benzaldehyde. It also, for XFs, tells us if we're interested in studying benzaldehyde hydrogenation, there's very little hydrogen evolution that's going to be occurring. So we can put it in the same cell and operate under very nice potentials without running into bubble formation that starts messing with our transmission. So what we do here is we see palladium's zanes, where again, we start with a palladium oxide because these are nanoparticles. We apply a negative potential. We immediately reduce the palladium to like a metallic palladium. We can see that from the zanes. And then we also reference it to a palladium foil. So the very nice thing about palladium is that the zanes can track whether we're a metallic palladium or either an alpha or beta palladium hydride. So unlike platinum and rhodium, hydrogen can intercalate into the palladium and form these hydrides. And there's a shift that's kind of documented here. It's if you're doing very quick zane scans of going from minus 0.4 volts or minus 0.41 volts, where it's mostly like a palladium metal or an alpha palladium hydride, kind of a low concentration of hydrogen, to a much, much higher concentration here, where you see this shift where it forms a beta palladium hydride. And so our thought was potentially why palladium is so good at benzaldehyde hydrogenation may be related to, well, it forms a hydride, and that hydride is very active. You know, platinum doesn't form a hydride. That was our hypothesis. But what was quite interesting is that, I'll just go back. So all we're doing right now is at a given potential, I'm just scanning the location of this peak here, right? We're doing these very quick, and then I'm just going to plot that peak location. So here what we can see, let's first just do with just phenol or acetate buffer around. You go to more negative potentials, you make this extreme shift in that peak. That means you're forming a beta palladium hydride, and it's occurring at the potential where you have enough hydrogen to go into the palladium surface and kind of form this hydride. What was interesting is that when we had benzaldehyde present, right, we did not form this beta palladium hydride, even if we went to really negative potentials. So what was kind of interesting is with the acetate buffer only or 100 millimolar phenol, where we know phenol really doesn't react very well on palladium, we could see the beta palladium hydride form. And if we went to any more negative potentials, we'd start forming tons of hydrogen bubbles. Those hydrogen bubbles mess with the transmission, and we can't get anything nicely in the signal. But with the benzaldehyde, we can go to like 200 millivolts more negative potentials. Because the Faradaic efficiency is so high, even though we're passing tons of current, it's all going to hydrogenate the benzaldehyde. We don't have any H2 bubbles forming, and we can get very nice spectra of this out to a very nice region. And we can see that no matter how negative we go, we were never able to see like a beta palladium hydride. So it's just still like, you know, a few percent of hydrogen put into the system rather than completely forming a phase transition. So if we just look at, again, the comparison, this makes sense that when we have benzaldehyde doing this electrocatalytic, doing the hydrogenation of the benzaldehyde to make the benzyl alcohol, we get very high rates, extremely high selectivities, but it seems to be occurring on the metallic palladium surface. It's not on a hydride palladium. So there's something else that's occurring there that we still haven't exactly resolved. But kind of the interesting thing is if we from XAFs, so not the zanes, but actually fitting the hydrogen to palladium ratio to get a rough estimate of what might be the hydrogen coverage, we see a similar thing to what we saw for platinum, in that as we go to more negative potentials, it's not a full palladium hydride, but we do start forming more and more hydrogen on the surface, and this correlates with the increase in the benzaldehyde hydrogenation rate. So we put more hydrogen on the surface. It's still a metallic or alpha palladium hydride, not a bulk hydride. And then that hydrogen can work very effectively to convert the benzaldehyde. So we see a nice correlation between what we call like kind of the coverage of hydrogen on the palladium and the reaction rate here. And then, of course, for something like an acetate, but immediately we completely fill it with hydrogen and it's still not very active. Okay. So the last thing I want to talk about is actually some work by that Johannes did recently that we've been thinking about a little bit more, where he tried to, on palladium, put both benzaldehyde and phenol in the same solution, and then they showed very nicely that, kind of interestingly, of course, palladium is very good at doing benzaldehyde hydrogenation. But what was quite interesting is that they showed if you put a little bit of phenol there, it actually accelerated the rate, which is kind of counterintuitive. And then eventually the rate started going down. So the picture with this is that you would assume that if you are doing benzaldehyde hydrogenation and you add phenol, that phenol should go to the surface and block sites and slow down the rate of the reaction. So that's what you see when there's tons of phenol around, no space for benzaldehyde, the reaction rate goes down. So this in your intermediate portion where you see some synergistic reaction rate was what they've observed. And they have some very nice work to describe why they think they would happen. But I want to just comment on why this enhancement could happen generally. So we've written a perspective a little bit about this, but let's break it down into, imagine we have some organic molecule, R1, that we want to hydrogenate, and another molecule, R2, that we also want to hydrogenate. So in this picture, let's say R1 is benzaldehyde and R2 is phenol, right? So what has been seen is that even from a Langmuir-Hinshelwood type mechanism, one can see that you get an enhancement when you add R2 to the conversion of R1. And so this is not an intuitive enhancement factor, because typically when we think about Langmuir-Hinshelwood, we think if you add something else in, it's going to block sites. It's always bad. There's a very particular case where it can actually, this R2 can enhance R1, and that only occurs when you have very high hydrogen coverages. So this is just plotting the coverage as you add more R2. So let's imagine we're in a regime where you have very high hydrogen coverages and there's not enough R1 on the surface. So this might be like, oh, there's so much hydrogen, benzaldehyde can't get to the surface. If you add small amounts of phenol, what they basically could do is they could clean up the surface, decreasing the hydrogen coverage, so you can put more of your molecule that you're interested in onto the surface. The reaction rate will go up, but then eventually the reaction rate will start going back down again. So this concept is what they observed in their system. But what we know, we know this cannot be the cause, because remember from when we did the Zanes and the XAFS measurements of palladium, we saw that the hydrogen coverage with benzaldehyde is very low, right? So this feature where we're covered with too much hydrogen, that can't be the case. So there must be another explanation for this reaction. And it's exactly what we think that they're saying, is that the phenol has some basically some hydrogen bonding that interacts with this and it's enhancing the reaction rate that way. It's not explained by coverages. So I'll pause there for the first break for questions. Then where we talked about this phenol hydrogenation following this Langmuir-Hinshelwood mechanism, and we can track basically its reaction rate by doing XAFS. And then also we see that understanding these coverages not only allows us to control rates, increasing reaction rates if we want, but also to understand why certain reaction rates respond to things like concentration, presence of other species, potential, all these kinds of things. So I'll pause to take any questions before I start into the next section.
Okay, great, thanks. That's amazing work. Are there any questions? Jerry has a question, or Jerry has a comment, I guess. No mic, so I'll ask his question. If a catalyst expert is going to start doing operando XAFs, what general guidance would you give them?
If a catalyst expert is going to be doing XAFs, what general guidance? Good question. I think ultimately for us, thinking about how to set up the system as similar to the reaction conditions as possible was really, really important. So it's really, we had to think about the cell and all the things we wanted to do with being able to control the potential, being able to control the flow rates, all these types of things. And then with the catalyst, there's a lot to do with the organization of like what would be the necessary beam path, all those kinds of things that needed to be considered. So it's like almost like you design a reactor for doing kinetics, but then you say, okay, how much of that can I translate to my system? Where like a lot of the limitations might be like the amount of catalyst that you can have there. I'd also recommend, really, we benefited a lot. I benefited a lot by working with John Fulton when I was there, who had been to the advanced photon source before. So if someone has not done that, I would communicate with the staff member at the wherever they're going to do the measurements. And like even simple things like, oh, this is how much space you'll have to set up the system, all those kinds of things. The last thing I think it was really important that why sometimes we've been unsuccessful in trying things is we didn't test out our rig or system before going to the beam line. So I'd like start measuring things, making sure everything works, testing it out like tons and tons of times ahead of time, just to make sure like all those kind of parts work. But I think like involvement or asking questions with the beamline scientists, what would be feasible? We used like, Hephaestus and things to make sure that like, okay, when our sample gets there, we'll have the right edge step. All those kinds of things were, I think, critical. And this was like, I think the second or third generation of the system that, we try something, it wouldn't work. So patience, I guess, is also a big factor. But I think it's a fantastic tool for getting some of this information. But I guess the last comment is if you can answer a question another way, I'd recommend using the other way because it's not simple. But I think it can answer some unanswerable questions otherwise.
Great. Peter, you had a question.
Yeah, I think it's almost connected to what you have said before. I was just wondering how much of the reactivity is influenced by the fact that you have an electron beam shining on your catalyst or also your reactant in this case, and whether you are able to really connect the kinetic data during the operando measurements.
Yeah, great question. So yeah, I guess we operando strictly defined would be we'd be quantifying all the products. So what we can do is, because the nice thing is since it's an electrochemical reaction, we can measure the current of the system. And that's like kind of a proxy of the electrochemical reaction. And when the beam was going versus not, it didn't affect the current that we saw. So from that perspective, we don't think there was a change in the system. What would have been ideal is if we were taking all our kinetic data in the identical reactor and then also doing it during the measurement. So we did not do that. We didn't do like product quantification. We saw like, okay, the product was there, but we didn't do a careful product quantification there. But because with the beam shutter like on or off did not affect the measured current at a given applied potential, we don't think it had a significant effect on the system here. But it's very hard to know. I don't know if that will be universal, and there might be small changes that we didn't detect. But that was kind of how we convinced ourselves, I guess.
Yeah, maybe just another very short question. So you also mentioned about the formation of the beta hydride phase. So you can form the vanadium hydride. And of course, this is known to be dependent on the particle size and the hydrogen pressure. So I wonder if you see any of these during your measurements.
Yeah, we didn't look at particle size dependence for that. I completely agree that I'm sure it is related to the particle size, but we only used a kind of purposely, we tried to make sort of similar particle size catalysts. We only studied that one. I can't remember. It was on the order of like 5 to 10 nanometers, but a pretty tight distribution. And that's kind of what we studied. I haven't done any I personally haven't done any particle size dependencies to see how this might change as you go bigger or smaller. But I completely agree. It probably would affect when these hydrides form.
Okay, I'm going to suggest that you continue and we can follow up with more questions.
Sure.
As we go.
Great. So I'm gonna do. So that was really the hydrogenation thing. Kind of related. I want to give one other example for electrocatalysis, just very, very briefly, that we've done. This is not on converting bio-oil, but this is us being interested in converting nitrates, which come from things like agricultural runoff from fertilizers. It's also an industrial waste stream, where we're interested in taking these nitrates that have a lot of negative environmental effects and then electrochemically converting them to either nitrogen or ammonia, something like that. And really the process is, again, very, very similar. Nitrate adsorbs onto a surface, reacts with some hydrogen. So a very similar concept to what we described, but now nitrate rather than inorganic is doing this. So that's the same process. So this is just the Langmuir-Hinchelwood mechanism, the same mechanism, but now rather than inorganic absorbing, you need to have nitrate on the surface. So I'll really quickly go through this, but we hypothesize nitrate reduction has the same phenomena, right? More negative potential, the reaction rate goes up, more negative current, meaning too negative a potential, you cover the surface in hydrogen, reaction shuts off. That's kind of the idea, right? And this is postulated like why this exactly occurs. It's how nitrate absorbs things, these kinds of things. But I'll skip all this and just tell you the XAFS portion. So this is now, we take platinum, we put it in our same, the same exact cell, maybe a different version of that cell, depending. And all we do is we look at different applied potentials while flowing electrolyte in. And this is the same case where we have the platinum foil, the reduced metallic platinum, so similar platinum nanoparticles. And we go to a very negative potential, so 0.05 volts versus RHE, almost all the way to evolving hydrogen. And all I'm doing is comparing where we have 0.1 molar nitrate in the solution, and then the other one only has the supporting electrolyte, which I think was sulfuric acid. So we can see really no difference in this. That's exactly what we'd expect. We do have some coverage of hydrogen on the surface, but there's not enough nitrate to do anything, so it's not affecting it. Now, what we notice, and just as I'll mention the kinetics for this one, we're at a negative enough potential that the hydrogen covers the surface, and we think that's why there's no nitrate reduction. When we go to a little bit higher potential, right, where we see nitrate reduction, you can see that when you have 0.2 volts, you still have a metallic platinum. It has tons of hydrogen on there. But at this potential, if you add the same concentration of nitrate, that nitrate is able to displace the hydrogen, get onto the surface, right? That's why there's less hydrogen here. And then this platinum oxide. We also did XAFs of this, and you start seeing some scattering that we may attribute to oxygen or nitrogen on the surface. And then the reaction starts occurring. So this is basically using the potential to go from these regions where covered with hydrogen, mixture of nitrate and hydrogen. And we didn't do it, but if you go to more positive potentials, you have nitrate on the surface, but you don't have any hydrogen, so the reaction rate goes down. So really, like, not terribly useful. So this is another application of that to another reaction, but the same setup, same utilization of using XAFs to try to understand what's occurring at a surface. So now I'm going to pivot a little bit away from electrocatalysis in that concept, but still in the concept of trying to understand electrochemical processes. And so we're really motivated by people predicting that there's going to be an increase in the share of renewable electricity. And what we think is a way to help with this is what are called flow batteries. So this is a stack of these flow batteries, how it operates. So you put a bunch of electrochemical cells together, you flow electrolyte through these manifolds that feeds into it, then you charge or discharge these systems, right, to store electricity. So at each full cell, each like little component here of the cell, you'll have a positive redox couple and then a negative redox couple. Those are two different electrolyte systems. And then the potentials of those will tell you how much potential you can get from your battery, all those kinds of things. So one of my students was interested in studying vanadium systems. So this is an all vanadium redox flow battery, probably the most famous or most widely deployed flow battery. So it's called all vanadium because everything is vanadium. You have one redox couple that's V2 plus V3 plus, one redox couple that's V4 plus V5 plus, right? Those are operating separately, separated by a membrane. You get the voltage between them, and then you do the redox kinetics, all these kinds of things, and that's basically how your battery operates. Now, when I started, we noticed that there's this redox couple called the cerium redox couple, cerium 3 plus, cerium 4 plus, much higher voltage. The higher the voltage of the battery, the more energy you get, the more power you get, the more efficient it will be if everything else is held constant. Because when you're operating this, a little bit of loss of voltage here, let's say 100 millivolts here, is very significant with 1.27. It's less significant when you have 2 volts there. So we were interested in this redox couple and wanted to study it. So what we discovered, reading through the literature, is that depending on the electrolyte, the redox potential of the cerium 3 plus, cerium 4 plus was very different. So in perchloric acid, which is known not to complex with cerium, it was very high. In something like chloride, it was much lower. And normally you wouldn't expect this, right? You have a redox couple, 2 plus, 3 plus, you put it in different electrolytes, it doesn't shift so much. It was a huge shift in its cerium. So basically from here all the way here. And you can see that has a significant effect on how you would use it as a battery. So we had 2 questions for cerium. One, why does this cerium 3 plus, cerium 4 plus redox potential vary? And a second question is that we've also noticed that when people were studying the vanadium redox flow battery, depending on the electrolyte they used, HCl versus H2SO4, they had different performance. So we had these two questions that we thought are related to how these metal ions coordinate with the supporting electrolyte. So is cerium 3 plus and cerium 4 plus, is it different in these electrolytes? And then we also thought maybe these vanadium ions associated with this one, maybe they're affected by whether there's HCl or H2SO4 around. So this is a perfect question in our mind for XAFs, because XAFs can tell us the structure of these molecules. So I'll just really quickly motivate why we care about this. Is we did a techno-economic analysis for basically the cost of storing electricity with the redox flow battery. And we see that if we do a sensitivity analysis where we say, okay, the redox potential of cerium 3 plus, cerium 4 plus, if it goes more positive or more negative, huge impact on the cost of delivered electricity, because basically you're getting, for everything, you're just for free getting more voltage, right? Similar for vanadium. This is even more significant than if you just reduce the cost of vanadium, all these kinds of things. So it really helped us understand having these high voltages, having these high efficiencies, this can have a very positive impact on the cost of storing electricity with redox flow batteries. So we really wanted to understand this. So we go back to our cell. This is the same cell. The reason we did a couple things. We like using the cell because it allows us to very, very carefully control the oxidation state of the metal ion that we're studying. So if you imagine like a V2 plus molecule, for example, it's very hard to keep it in the correct oxidation state, but with an electrochemical potential, we can do that, similar to cerium. And then we just hit it with an X-ray beam. And in this case, we're not interested in the electrocatalyst. We're interested in the ions in solution, right, to understand their structure, right? So these are not the electrocatalysts anymore. There is an electrocatalyst, but we're not interested in studying it. The other thing we did is molecular dynamic simulation. So we took, this is like a vanadium ion, let's say, that we put into there, and then we let it, maybe you guys can see the video, jiggle around with the water there. And the beautiful thing for this is that you can take this molecular dynamics, you can take the snapshots, and then you can build up an XAF spectra of this to do comparison. So that's what we did with this. So let's start with just the cerium. And what we saw is that if we take a cerium 3 plus oxidation state and tried it in a bunch of different electrolytes, there was fairly negligible changes in the local coordination for that cerium ion, right? So we know it's cerium 3 plus oxidation state. We put in HCl, all kinds of different things. None of them really had a significant effect on the local coordination number, bond distances. And I don't show it here, but we also did UV vis of all of these electrolytes. The UV vis also said there's no real change there. So basically in all of these, by doing the fitting, the cerium is coordinated by 8 or 9 water molecules. This bond distance matches what we'd expect. It matches the MD XAFs, all these kinds of things. This is really the structure of these systems. This is coming from fitting the cerium oxygen shell in sulfuric acid. All the distances we could kind of capture from this. So this is the dominant complex in cerium 3 plus. What was very different is that the cerium 4 plus, the higher oxidation state, when we tried to fit it in, for example, sulfuric acid, we saw that, yes, it is coordinated with water, right? On top of that, it seems to be coordinated in sulfuric acid with some so there's some sulfur scattering that we attribute to when we do all of this kind of fitting together and look at these regions, that unlike the cerium 3 plus, it's not only coordinated with water, it's also coordinated with sulfates or bisulfates. So bisulfates because that's the dominant species there. We really can't distinguish if it's a sulfate or bisulfate. We just assumed from the XAFs because the proton really doesn't affect much things. But what we're seeing is this cerium oxygen. Several of these oxygens are not actually from water. They're from the bisulfate anion, right? And we're sure about this because we also see the scattering from these sulfur groups that are a little bit away at the exact right distances. So this is not completely misunderstood, but it allows us to really get a picture of these systems. So this gives us, uses that. So what was interesting with this is we say, okay, well, what's really happening? We have this cerium 4 plus, and it has a certain anion around, and it can go from the cerium 4 plus with the 9 water molecules, coordinate with these bisulfates, and that will have some free energy to it, right? Because obviously if the sulfate wants to replace the water, it must be favorable. So what we did is with some collaborators, Brian Goldsmith, they did calculations for all these different anions, right, that we'd looked at, how strongly do they complex with the cerium there, right? So you can see certain things like chloride complex very strongly with cerium 4+. And as a reminder, none of these are coordinating with cerium 3+. They're only coordinating with cerium 4+. And we can get these free energies. Now, these DFT free energies, we can relate to a redox potential shift. So remember, in HClO4, here's cerium 3+, cerium 4+. And what's happening here is as the redox potential shifts more negative, it's because the cerium 4+ free energy must be changing in that electrolyte, while the cerium 3+ is staying the same. So redox potential in electrochemistry from the Nernst equation is just, it's basically a Gibbs free energy of a reaction. So this, where it shows up here is telling you the Gibbs free energy from going 3+ to 4+ is changing. And if we just plot these experimental values, we see we get very nice agreement with this concept that the cerium 4+ is just coordinating with these species. So because we know they are coordinating from XAFs, we know what's coordinating, it matches very nicely our DFT. We have a good picture of what's actually occurring in this system, right? So I'll pause for the second break for here. I hope this is about on time. Just the small portion where I talk about the nitrate reduction, and then also for the cerium redox couple, we detected the structures by XAFs and then kind of use this to understand and explain why there's this shift in the electrochemical potential.
Great, that's wonderful stuff. Are there questions? If anyone has anything, I'll ask. So did you do similar studies with chlorine, and do you see similar effects with?
I think we did with chloride, and we did see some scattering for that one. I don't remember offhand, like I didn't put it in this slide, but we did a few different electrolytes for cerium 4+. Cerium 4+ was a little tricky to do some of the spectrum because it's very hard to keep it 100% as the cerium 4+ oxidation state. So some of them, because a lot of them we prepared them before we put them in capillaries. This was around COVID time, so we were doing a lot of shipping in. We would take a spectra and realize it's a portion of it is in cerium 3+, and so it was really hard to fit, the spectra nicely. But we didn't do all of that. We did, once we kind of confirmed a couple of them with DFT, that's why we did most of them with calculations.
Okay, great. Anatol, you have a question?
Yes, I have a question about sulfur. So can you please show again what's the evidence that sulfur enters second shell?
Yeah, so our thought really was more from the fitting of this feature where we fit the cerium 4+ structure with a few different spectra where we had this, let me see, basically this scattering feature of the cerium to this sulfur group a certain distance away, included as a path. And then we compared this basically with and without this group and looked at basically the quality of the fit here. So the bond distance from the cerium to this sulfur kind of matched where we'd expect from this. And then we took this structure from DFT and did molecular dynamics of it and kind of saw that there appeared to be this additional kind of feature that we attribute to this sulfur scattering.
In the initial stoichiometry of the sample, was there enough sulfur to coordinate each cerium?
Yeah, because we have very low 0.05 molar of cerium 4+ and then 2 molar sulfuric acid. So we have very, very high concentrations of the sulfuric acid around, for this.
And that was also modeled by ab initio molecular dynamics?
I think in the MD, I think they purposefully put in, I believe they put in this amount of the sulfurs and kind of kept it fixed in the MD. And then I think around it might have been water though. There wasn't additional ones there. So for like so it's not like the second coordination shell. It's just the scattering of the sulfate that's coordinated directly to it. Okay.
Thank you. Thank you very much.
Yeah.
Okay, that sounds great. Why don't you continue and we can have some questions at the end.
Okay, so let me go back. So then this one is, so as I mentioned, we studied cerium and we did some work on that. We also were interested in vanadium. So this is a vanadium complex, right? So as I mentioned, the motivation for this is people had studied vanadium redox flow batteries and found that the efficiencies seemed to be better when you used HCl compared to sulfuric acid. So there's other reasons for that in terms of solubilities, but we were interested if actually the reaction rate of going from V3 plus to V2 plus could be better because of the chloride content. So on the top here is molecular dynamics of a vanadium completely coordinated with water and then to sulfate. And then here's our spectra of just adding higher and higher concentrations of sulfate into the solution. And in this case, we referenced it to vanadium 3 plus in perchloric because we know perchloric acid really doesn't coordinate it. So it should be purely water in that system. And I don't think I'm going to show any of the V2 plus data, but V2 plus basically doesn't coordinate with any of these electrolytes, as we did a lot of UV vis to be sure of that. Okay, so this one is a little bit more took a little bit longer for us to convince ourselves, but basically what we see from the molecular dynamics is that in certain regions, as we started adding this sulfate into the system, there was shifts in kind of the features that if we backed out are associated again with this sulfur in the sulfate that's coordinated to one of the vanadiums. And then as we add more and more sulfate into our solution, going to higher and higher concentrations of sulfate, we see also a similar type of effect in our experimental X-ray absorption. Okay, so our picture is that here's the sulfate in this coordination here, and then we don't think it's 100% this species, but we think some of these sulfate or bisulfate coordinated species are present, right? In addition to just the purely water coordinated system. So then here is our XAFS, basically the same result, so that's the same type of study, but rather than sulfate as the anion, now we have chloride as the anion. And we did molecular dynamics for, of course, the pure one, where there's no coordination at all, it's only water. And then whether it's coordinated by 2 chlorides or 1 chloride, and then we increase the concentration of this. So really similar, we saw similar features when there's a difference between if it's coordinated by the oxygen in the water versus the chloride around here. And we see some changes as we go into more and more chloride that tells us that possibly what we have here is some mixture of chloride coordinated and, sorry, 2 chloride coordinated and 1 chloride coordinated vanadium species. We don't believe this is the only species there. So there's still also some water based on the coordination numbers. It's not like this is the only structure there. It's probably a mixture of this. But we do have some evidence that, okay, as we go to really high concentrations of chloride, now this chloride can go and start coordinating with the vanadium. Okay. So in addition to, we only did this for chloride, but we think this is a general phenomenon for things like hydrobromic acid, hydroiodic acid, other kinds of things, right? So this is what I mean by X here. So that's going to conclude that portion of the XAFS talk. I'm going to talk a little bit quickly through the kinetics of this, which is really, there's not going to be any more XAFS, but I'll talk about what I mean by the structure of these molecules being affected by, which we detect by XAFS, influences the reaction rate. So here I'm plotting what's called an exchange current density, which is basically a way of measuring how fast vanadium 2 plus goes back and forth between vanadium 3 plus. So it's very similar to like an electrochemical rate constant. Higher rate constant, vanadium 2 plus can go to vanadium 3 plus more rapidly, and same for the reverse, right? So we can see here from our very careful studies is that as a function of how much vanadium we have in the solution, in HCl, the reaction rate is faster, right? And the activation energy is lower, right? So when you have hydrochloric acid around, vanadium can convert back and forth in oxidation state more rapidly. And then what was interesting is that if you go into HBr, it's even faster. And in HI, it's even faster, right? So higher exchange current density, lower apparent activation energy. Okay. So one other interesting thing is that if we take this HI and we measure the reaction rate, and what we see is that as you add small amounts of sulfate, the sulfate basically poisons the activity of this system. So in pure HI, we think vanadium is coordinated with a little bit of iodide, but as soon as you add some bisulfate around, that bisulfate basically displaces the iodide, and now you only have vanadium sulfate, and then the reaction rate goes down. So this is the exchange current density as we're basically poisoning it by changing this complex. Okay, so this is kind of those results there. So our picture here, and then I think I'm a little bit low on time, so I'll make this the last portion, is what we think is happening is if you're converting between a vanadium 2 plus and a vanadium 3 plus, really this anion, this halogen anion, is acting as a bridge when you're doing the reaction rate. So this is a concept that's this bridging mechanism that's known for inner sphere reaction systems. But we found that the ordering seems to be related to how strongly this bridge forms here. So chloride versus bromide versus iodide, when that species, like the chloride there, adsorbs onto the catalyst surface, it'll do so with different energies, right? And then this energy might be related to those kind of reaction rates. So our picture with this is that if it's purely the bridge energy, then the activation energies that we see and the frequencies factors that we see match this energy here. And particularly when we add this sulfate in, the sulfate binds the most strongly. So it kind of takes over from the iodide activity. That's what's happening. If it was purely just how much anions are on the surface, when we added that sulfate in, iodide by itself binds much more strongly. So it doesn't really match this ordering. So really, we think this picture on the left, where these coordinated complex forms, we see them in the solution via XAFs. We think they also form on the surface, and their energy is important. Now, the limitation we have with the XAFs is we can't detect these surface species so far, right? We've had a lot of difficulty with that, but we're kind of basing that we know they can form in the bulk solution, and then we do simulations that say they might also be able to form on the surface. That's kind of motivating this study. We've also used this to design better and better catalysts that have a higher activity. I'll skip that because it's not really related to the structure at all. And then I'll just conclude with our summary of the redox flow battery work, where we study the cerium. We try to detect these small concentrations of species that we think are very, very important for the overall kinetics of this system. This between this one and this slide are kind of the summary of all the different topics. I'll just acknowledge the people that were completely important for doing this, and then I'll go back to this slide on the kind of the three things I touched on to take questions with our remaining time.
Great, thank you so much. That was really wonderful. While people are forming their questions, I'm going to let Anatoly come back and tell us about his short course that he's running.
Oh, yeah.
Anatoly, you want to?
Thank you very much for this opportunity, Matt. I did not know you meant that I will do it for everyone. I thought just for you. But of course, I'll be happy to do it. But maybe I can first ask question to the speaker, or you prefer that I first tell about the person?
Whatever you want. Go ahead, Anatoly.
Just a quick question. Thank you very much for this talk. And the last part, I think it relies the conclusions that you make about the role of halogen or sulfur for bridging the catalyst to the electrode. I think it relies on this observation that this ion, sulfur or halogen, enters the first coordination shell, right?
Yes, right. Yeah.
And if I remember correctly, this depends on your interpretation of this very small change in the intensity of XAFs in the first shell.
Yeah.
But is only intensity going to be affected? For example, sulfur distance to vanadium probably will be longer than vanadium oxygen, but it doesn't seem like there is any effect of that. So maybe.
Yeah, we did do fitting of it as well. That kind of roughly. I mean, it's very tricky because it's not. It's like a small fraction of it. So we see features that seem to be similar to where the distance on the sulfate should be. The chloride, when we do the fitting, it is the chloride, the vanadium chloride bond distance or scattering distance is different than the one we get for the water when we do the fitting, and kind of matches where we think it's there. I agree. It's not as clear as if it was completely coordinated. What we've also done is UV vis measurements under the same conditions that also show a shift, and we did time-dependent UV vis that says this is the direction that we shifted. And I think the particular thing is that as we increase more and more chloride, the fact that the UV vis peak kind of shifts in that same direction, combined with the XAFs, gives us a little confidence. But yeah, there's still a lot of uncertainty to the exact distances, right?
Thank you. I think Yulia has a question, and then maybe I have a minute left. I'll talk about
Okay. Yes, Yulia, please.
Hello, everyone. Yeah, very interesting talk. I have actually a general question. So where did you, like, how far you got with the cerium-based flow batteries? Do you think it's like commercially viable, or like I didn't get the like final conclusion?
Oh yeah. So I think right now the two challenges we saw from, I'll say from the techno-economic analysis, I'm not trying to commercialize it, but is the current densities of them are not at the same level as like other ones. So you can't run the reaction as fast. I mean, not to say you never will be able to, but like the current density we saw, it was hard to get them to that level. The other problem was because of how high the redox potential is, which is good. It's good that it's a high redox potential, but it also makes it such that the electrodes you have to use need to be very stable. So typically for an all vanadium one, you can use carbon as the positive electrode. For the cerium, really the only thing that's stable is something like a platinized titanium, which is enormously expensive. So if you could develop a very stable, low-cost electrode to use for that, it'd be much more compelling. To be frank, the student that was working on it graduated a couple of years ago, and that was going to be our next direction. And it's so we haven't really pursued it, but that would be kind of the direction we want to take, is push the voltage higher, develop an electrode that was lower cost that could be used for it, and I think it would be hypothetically competitive with it. But really, there's not nearly the development of it from an engineering perspective compared to the other systems to say like, oh, it's going to be commercially viable right now. I say it is used for a completely unrelated thing, like cerium, because of its high redox potential, is used as like an oxidizing agent, things like that, for tons of very useful stuff, but not super heavily for redox flow batteries, from what I can tell.
Okay, Matt,
Okay, thanks. Yeah, so Anatoly, so I think we'll wrap it up here. I'm just to come back to Jerry's original question about how to ask for help and on this kind of stuff. There is a short course that will be taking place at Brookhaven Lab that Anatoly's and his synchrotron catalysis consortium are running. It happens every year, but the application deadline is actually the end of this week. So visit BNNL SCC course if you're interested. And
thank you, Matt.
For more just
thank you, Matt. Can I say just a few words about it if people are still around? Can you hear me? So if I can even share the screen, it will be useful. But just one thing I wanted to say about this is we've been running this course always with a focus on XAFS for the last 20 years. And what made the most sort of common theme for these courses over 20 years was that they were aimed at solving problems, structural problems primarily, in different type of materials, different type of complex environments. And this time we decided to change the theme, to expand from solving structural problems to solving problems more related to mechanisms. And in catalysis, to address the mechanisms, you cannot just focus on one technique. You need to understand also how to run experiments under realistic conditions, and also how to combine different techniques, including techniques that are available in the large user facilities. So in this course, we will cover aspects of in situ characterization using X-ray diffraction, electron microscopy, and I'm going to show you a brief agenda, and also XAFS, of course. And there will be a practical session on the last day. You can find the agenda online. And in practical session, because this is a new course, we will do what we have done in the last 20 years. We will focus on helping people solve XAFS analysis problems related to nanomaterials and catalysts. But in the future, we'll probably incorporate also training in combining techniques and doing operandi studies. And thank you very much for this opportunity to give this advertisement. And thank you to the speaker. It was great talk today.
Thank you.
Okay, great. Thanks, Anatoly. And let's all thank Nirala. That was a wonderful talk. I feel like I learned a lot. Thank you very much. And I'll stop the recording now.
Yeah, thanks, Matt. Thanks, everyone.